Well, last week's presentation was a little bit disorganized and technically dodgy, but this week's presentation will be a little bit disorganized and technically dodgy. So the first thing that I want to do is follow up on a thing from last time, which is the, excellent, maybe excellent, yeah, good. Follow up on a thing which is the resonant filter as a feedback network and what you can, well, I'll just show you how you can turn that into an oscillator. And why is that interesting? Well, it's interesting because the specific thing that you have to do in order to make a filter be an oscillator is to introduce some nonlinearity into the interior of the oscillator. And that was a thing that we sort of started looking at last time, but which I want to develop further this time, because in fact, the most interesting filters are the ones that have nonlinearities inside them. There seems to be a huge collection of possible such filters, of which there will be two that I hope to get into today. That one and what are called Slew Generators, which are another very simple kind of filter with a nonlinearity inside it. And the thing about both of those things is that the nonlinearity can't be taken out of the filter. It belongs in the feedback path of the filter. And so you will not be able to make, for instance, well, you'll get it, you'll see. You can't figure out what that is by thinking about it is not the same thing as taking a linear filter and adding a nonlinear element to its input or its output. The fact that the nonlinearity is in the recirculating part of the filter is essential to how the filter operates and how the nonlinearity enters into the situation. So to that effect, what I will do to start with is just sort of get back to where we were, which was making, is it called files? Oh no, wait. We'll get there. Okay, so what happened last time was large numbers of stuff, but in the end there was this resonant filter. The way we got to the resonant filter was by describing it as a reverberator and then changing the room to be one sample big. A sample, by the way, what's the distance in air that corresponds to an audio sample? Anyone? Any takers on that?
Depends on the sample rate.
Oh yeah, it depends on the sample rate. So I guess I'm assuming sort of the typical 40K-ish sample rate, so that Nyquist is 20K. So a sample is a 40,000th of a second, and a second is about a millisecond is a foot in sound motion. That's the way to remember sound and light is sound moves a foot in a millisecond and light moves a foot in a nanosecond. And vive la différence. So we're talking a 40th of a foot, which is about a quarter inch. So a quarter inch is about the amount of air that's one sample at CD rate. Just so you know. So what we're doing is we're making a filter which is a room that's a quarter inch on each side. Yeah, not exactly, because the other thing that we're doing is messing with the signal as it goes through by rotating it. So this is yesterday's patch. Actually, this is last week's patch. This is the active ingredient of what was going on last week, which is stuff. Hey, oh no, are we getting this again? Okay. Well, it's just to keep us entertained. What is happening? Wow. Okay. I think okay, come on. Quit mousing. All right, very good. Small block size. Go away, you. There we are. Okay. Okay, so what happened last time was we ended up wanting two delay lines because various ways of dealing with telling you why this is. But one reason is because we want to have a point moving around a plane instead of a point moving on a line, because when things go through zero, they don't have any amplitude, and we want to be able to have things have amplitude constantly. Or another way of putting it is, we want to, the thing that is oscillating is effectively a rotation. Oscillatory motion is just something going around something else. And you need two dimensions to go around a thing. This is topology. You can't go around a thing on a line segment. It can't be done. Or to put it another way, which will be germane a little bit later in the quarter if I get this far. If you think about it as a flow, so think about a pond with water in it that's circling around. Well, if you drop something on the surface of the pond, the something will circle around. But if you, and how do you describe that circling? You simply say that it's a differential equation. It's a system which you describe by its motion in time. Wherever the point is, you ask how fast is the water moving at that point where the thing is. And then you allow it the next instant to be a little bit, an instant's worth of motion in that direction, and then you keep going. And there are theorems about this, and we'll get into it later. But if you think about how that works on a line segment, if you want to have a flow that moves something back and forth on a line segment, it's a contradiction in terms, because wherever it is in the line segment has one direction and one speed at which it is going if it's just a flow. So you can't have a circular flow, because you would have to be able to get the same point to go left at one point and then right at some later point. So things that are resonant inherently have to have two dimensions at least of possible motion. Or to put it another way, they would have to have 2 degrees of freedom. Or, there are other ways of describing that. But, all right, so we decided to have our 2 degrees of freedom be represented by 2 separate delay lines, TED1 and TED2, which I could have called horizontal and vertical or something like that. For a reason. We could have used one delay line and simply used a delay of length 2 if we wanted to, instead of having 2 delay lines of length 1. But it turns out that for what we're doing here, it's far superior to organize it as 2 single delay lines than it is one longer one. Right. And just to quickly go back and talk about what's going on here. I was making. Let's go get Inkscape out. I was making diagrams that were showing what the motion actually was like, which is something like this. See if I can find this. New document. And now we're going to open recent. And we're going to get the most recent thing. We're going to get a reasonably recent thing. What was that? Oh, here it is. All right. I don't remember what this was about. This is, I was talking about rotation, wasn't I? Okay, there it is. Anyway, here, these 2 axes are what is in the delay line. This delay line is only 1 sample deep, so each one of them has one number in it, at least, that's the right word, conceptually. And so what's happening is we're taking whatever the thing is and moving it around the circle. But another way of describing that is, this is a circular flow. Now, I'll start getting risky and use my pad here. It's a circular flow. Don't really need the axes to describe it, but I want to do this. And the circular flow is, one describes it as a vector field or just as a thing which is wherever you are, you have a particular direction you're flowing in. And if you make a flow that looks like this, well then the object, the stick or whatever is floating around, will just do this thing forever. Of course, if you had a flow that looked like, if you had a flow that looked kind of like this, then you would put something down and it would just go further and further out, and then the thing wouldn't oscillate stably. So there's something about designing things that like to oscillate stably that has to do with making things move in a contained way. And you can put various kinds of what's the right word? You can put various. Well, you can gild the lily in a lot of ways. So. Of course, the way this rotation operation works is that there's a flow at every possible radius, and at every possible radius, the flow basically goes around in the same kind of circle. Furthermore, the flow is faster, which means these arrows are longer, if you like, the further you are out from nothing, or from the origin, from zero, in such a way that no matter how far out or no matter how close you are to the center of this flow, you'll end up taking the same amount of time to go around the thing. And here's where it gets interesting, because that's only one particular kind of flow. You could easily design other kinds of flows that had different speeds of rotation at different radii, in which case you would have a filter whose resonant frequency changed depending on the amplitude that you stuck in it. Okay, so suppose I this is getting down to why this course is about an interesting subject. Whether or not the course is interesting, the subject is. Okay, so what I'm saying is, if you could, this is just this is a way of this is a kind of motion, which it's a flow. If I fixed the flow so that the arrows were larger here comparatively to here, and here I have to be a little careful. To get the uniform behavior, the flow has to grow linearly as we get out from the middle. In other words, if this thing is going 1 mile an hour, this should be going 2 miles an hour, this should be going 3 miles an hour. And if that were true, then no matter where I started out, I would take the same amount of time to get around the circle. But if I went and changed that, because this is just equations we're writing down, we can make anything that we want, right? I could make them longer here comparatively and shorter here. And then I would have something that if we were going around here, we would be traveling faster than if we were going around here. And now if we regard this as a filter, so what a filter is the same thing, it's a flow, except that we get to add, what's the best way to think about what we add? We get the thing itself is a motorboat. And so it's not only following the flow, but it's also got its own little bit of motion that we can specify, either up and down or right and left. Well, then that's a filter, and in fact, where the boat is going to look like it's related to where we drove it, but it's also going to be doing this. It's going to be resonating, right? And so for instance, if we decide to pump it with, should I just do this? Well, okay, I'll do this in a second. So if we drive around in such a way that we get out further from the thing in a situation like that, the pitch would go down. And then if we then took it and sort of worked its way toward the center, then the pitch would go back up. All right. Now, what I've done here is drawn a what's the right word? A critically stable or a critically unstable filter. I'm not sure if I'm using that exact terminology. In other words, this one is a thing which will resonate forever. All you got to do is give it one impulse and it will keep going forever. But of course, a flow that would correspond to a reasonable filter. Let's see. I'm sorry. Let's do save as, because I need to start another blackboard here. So this is going to be number 4. All right. And now what I'm going to do is I'm going to get. Oh, good work. Yeah, we don't need that anymore. It's great. You can do anything if it's just a file and nobody gets physically hurt. All right. So I'm going to keep this around because. Oh gosh, but how am I going to get? Oh, I see. I'm just going to take the whole thing and move it up top. And then just keep working. Now, what was that? Oh, dear. That belonged somewhere in the picture. It's not a very good x-axis anyway. All right, very good. Okay, so this is another filter. This is the filter which, no matter what you do, it just blows up, right? And here is okay, back to trying to draw this. So we can get the draw tool. So here now is a filter like this one, which is what's the right word? Which is stable and in fact damps. If I can draw this right, I'm going to draw 4 of them first off, and then maybe draw the others there. I don't know if this is clear, but what I'm doing is I'm tilting all the arrows somewhat so that yuck, sorry, not doing this terribly well. So I'm tilting all the arrows so that they all sort of push us not only around but also in toward the middle of which is, by the way, a point which doesn't have any flow at it. It's just sitting there. And then what would happen is if I put myself somewhere, or if I put an impulse into this thing, the thing would make a geometrical spiral, say. I mean, in the simplest case, a geometrical spiral into the middle of the flow. Or sorry, into the middle of the pond, into zero, into quietude, into the place where we're not moving. Right. So this is a stable filter, and there's an example path through it. And here's a critically stable filter, and here's an unstable filter. Well, actually, this one's outrageously unstable, but you could imagine that we just had these things tilting slightly outward, in which case, as soon as the thing got off the very middle, it would start to spiral outward, and it would spiral outward until the universe vaporized, or else until we reached the extent of our digital analog conversion, whichever came first. usually the analog digital converter prevents the universe from vaporizing by not being able to give us those 10 to the 38 kinds of numbers. And that's a good thing, because otherwise I would have vaporized it many, many times. All right, so there's actually not the whole universe, just about the galaxy. Okay. All right, so with that in mind, what this last patch from last Monday was doing was taking whatever was going in, rescaling it, and then giving it a twist. So these 6 objects are a complex multiplication, or they are a rotation matrix, depending on how you want to think about it. It's a rotation matrix for now. And here is the numbers in the matrix are the cosine and sine of some angle that we will specify. And then, just to keep ourselves sane, we clip it. Oh, well, we throw in the inlet. So this is the external, whatever external motion is imposed on the thing or added to the filter zone recirculation. And then just to make sure we're cool, we clip it to some finite value and then feed it back around. And meanwhile, enjoy the output. Okay. All right. Well, and just to get this back in your heads, and also so that I can see if sound is working, I'll just feed this a nice sound. Okay. First off, we have to choose a number here. So let's choose 99. 99 out of 100. Which means almost going straight around, but not quite. We're letting it decay somewhat. And now the deal was I was going to put oh, you're right. Oh, I have a nice noise generator here. That's exactly what I want. And now I want to listen to the output. Why don't, oh, right, and of course the reason I don't hear anything is because I haven't done the usual thing of seeing if we got output. Output. Okay, and now we'll put this back up. Oh, and give it a. Oh, yeah, right. That's the thing. All right. So that's as far as we got last time. Okay, and that is this thing here, if you like. Okay, questions about this? Yeah.
Why were we only feeding back into the X coordinate?
Were we? Why were we only feeding back into the X coordinate? I think. Okay, so this would be X and this would be Y.
Yeah.
So there are 2 feedback paths.
Oh, right, gotcha.
You don't look convinced.
Maybe are you referring to what's happening from the inlet?
Yeah, that inlet.
Oh, why am I only putting something into that?
Yeah, sorry. Okay.
Well, all right. So my answer to that is the signal that I generated was real valued, and I only want to add a real valued signal. But that's not really an adequate answer because I'm listening both to the real and the imaginary part of the output. So that is a bit of a hand wave. Another way to say it is I could easily put it into the other side or to both. If I put it into both, then I'd be pushing at a 45-degree angle or whatnot. Or if I had 2 signals, then I could possibly fruitfully use them both in some interesting way. Like, for instance, if someone gave me the output of a Hilbert transform that was already in quadrature, then maybe a good way to pump this filter would be to pump it in quadrature. Possibly. Other? Yeah?
Last week, this was a reverberator, and we turned it into this resonant filter.
Right.
What did you change to do that?
Oh, what did I change so that this was no longer a reverberator and is now a resonant filter? What I did was I changed the delay time to 1 sample.
Oh.
So before the delay times were maybe 30-ish milliseconds or something like that. And there's a thing about that too, which is that I could go back and make these delay times 30 milliseconds and a different kind of thing would happen. Oh, yeah. This would be that would be what's the right word? That would be a digression. And when I digress, or when I'm in danger of digressing, then the correct thing to do, I've just realized, is to suggest that this would be an interesting topic for you to explore on your own. But to tell you in words what it does, or what it might do, which is to digress, if you made the thing be, say, a millisecond long, then that's the same thing as having the thing operate at a sample rate of 1 kilohertz in one sense. And so what that means is you'll have a resonance somewhere between 0 and 1, and whatever that Nyquist is, 500 hertz. And you'll have another aliased one starting at 2 kilohertz, and then have another aliased one, and so on like that. And that's what we call a comb filter. So we'll be back to comb filter land at that point. All right. Okay, and then the other thing about this is, let's see, we've got it. Okay, now, right. Is this a good idea? Let's see. I don't know if this is a good idea or not, but I'm going to do it anyway. Let's just verify that thing is still there. And now I'm going to do this thing. First off, I'm going to try just making the thing critically stable. And now I can disconnect the source if I want. And now I've got an oscillator. And the oscillator still will do this good thing. In fact, I can even modulate this as audio rates if I want to. And that will work perfectly. And then I can have FM, for instance, or whatnot. Okay. Furthermore, theoretically at least, and actually practically it's almost true, that whatever amplitude the oscillation has, that amplitude will still be in there for as long as I maintain the feedback at 100% and the don't put any extra input into it.
No, why does it have the timbre that it has?
This is a sinusoid.
Really? It also didn't sound like
If
that
it's
when
not
you
a
were changing the
sinus...
frequency.
Oh, really?
But there's no extra input.
Yeah.
I mean, it sounds reverberating.
Interesting. It does.
Am I the only one?
Well, there's a thing. When I do that, you're going to hear the fundamental of those notes, and then it's going to be hard to hear that as a sinusoid. But the room is reverberant, and you're also hearing the sinusoid reverberate. I don't know. Sinusoids are more, I don't know. Sinusoids are not always what you think they are. Have you noticed that if you listen to a sinusoid and turn it up, the pitch goes down? You don't know this? This is a basic fact of psychoacoustics, which you should all have learned in 270B. Okay, so now I'll choose a nice pitch here. This is probably all right. Now I'll get it a little bit louder. Now just listen to whether you think it goes down in pitch or not. It went down. There's actually a possible explanation for that, which is that it could be that, well, all right, all right, for further exploration, why do you think that happens? If you actually think about how the cochlea works, you can explain that. Sort of. Hand-wavingly. And in a way that no one could ever determine experimentally was incorrect. So you can go around saying it then after you figure it out. Right. Okay. Sorry, that is a digression on a digression. Other questions while we're at this? Okay, so what I want to do now is...
Could we try, and just because it would only take 10 seconds to do, like if we just patched in an OSD filter?
Oh, good idea. In fact, we already got one right here. Oh, this is it. This is for comparison's sake.
Oh, right.
So there's my thing, and here's my sinusoid. And does this do the same thing when I start squiggling it around? Yeah, it's louder than the other one was, but other than that...
I think it's the onset that's shaping the timbre.
Oh, yeah, the
So
transitions.
onset, it tricks your brain into thinking that it's it has more higher frequency content, I think.
Yeah. Or maybe that whole thing about harmonics contributing to timbre is a lie.
Yeah.
now I'm... Okay, so here's another possibility. What if you took this thing... Let's see, all right, so this... Oh, rats, what am I going to do? Okay, so what I really have to do now is I have to take this thing and do a save as mess so that I can get this into this week's patches, because this is one of last week's patches. Did I even make the directory? No. Okay, and now I'm going to save this. Did I do something?
So this is critically stable, that only at Unity Amplitude it's stable. If you go above it...
At Unity Feedback Game.
Yeah. Unity Feedback.
Mm-hmm.
If you go up, it goes up. If you go down, it dampens.
Right.
So I'm going to show how to calculate the Unity Amplitude for some other, if you're designing some other ones.
Well, in special cases I can, but I'm not sure. Think about that. There's sort of a general answer, but the general answer is chasing poles around, and then we're doing it like engineers, which would be a different course. But at the same time, things like this, where you sort of make essentially conservation of energy kinds of arguments, can get you an awfully long way without having to go into the pole plots. So I'll try to do that as much as I can. Yeah. Okay. All right. So you all know what will happen if I push this above 100. Oh wait, I'm still doing the save as. Save as, please, and we'll go here and make. Oh, I forgot to make the directory. Yeah. Or maybe I made the directory in the wrong place. What? Oh, come back here. Oh, here we are. No, not here. Okay, and now, what am I doing? Okay, now I'm going to do, now try this again. Save as, oh, we're in 3, we're going to go back here, there's a 4, and it's going to be 1.resonant, and then I'll try to make a better name for it later. And then also I need output. Is that the only abstraction I'm using? I think, yep. So I'm going to say, oh no, that was a bad move. How about, let's just do this. And then I'll just resave this, and we'll hope that I didn't do anything worse than what I actually know I just did. Okay. All right, and are we still working? Probably. Yep, we're good. Okay, so next thing is this. Going back to this picture. Actually, I have two classes of things to talk about. One is kind of classical, and the other is a little non-classical. So the classical one is this. If I fixed it so that, so still talking about flows, so if I fixed it so that for small radii, the flow was pushing outward. For medium radii, the flow was conserving, that's to say going around in a circle. And for larger ones, the flow was pointing inward. Then there would be what's called a stable cycle. And furthermore, the way I've drawn it, that would be the only stable cycle. There would be one messy problem, which is that there's still always, for topological reasons, going to be a point in the middle that isn't moving. There's a theorem about that, but I can't quote it right now. I can't. It's some fixed point theorem. And under all the correct conditions, you can at least set up conditions whereby you can say it's always going to be the case that no matter where we start in this plane or in this flow, if we call it that, eventually the thing will cycle into this limit cycle and stay thereafter forever, right? This in the mathematics textbooks is called the predator-prey. Is it called the predator-prey equations? Except I don't think there's any specific kind of equation, so it's a predator-prey kind of a situation. It's a flow in the plane. So a flow in the plane just means any situation where you draw the arrows anywhere that you want to, going back and well, not back and forth in the same place, but any function of position that shows you what the velocity is, that will be a flow. And under certain conditions, flows don't have any choice but to find their way to a limit cycle like this. And the what's the right word? The analogy, the metaphor, I'm not sure if that's the right word, that people give young mathematicians is this is like rabbits and foxes in a preserve or something like that, or in the forest, right? Because the thing, and what you say is this is how many rabbits there are and this is how many foxes there are. Because if there's a bunch of rabbits, then the foxes got a lot to eat. And so then the foxes go up. But then when the foxes go up, the rabbit population goes down because they're getting eaten. But then when the rabbit population is low, the foxes don't have anything to eat, so their population goes down. But then when the foxes are gone, the rabbits start multiplying. And this, I think I've read that people have actually observed this, but I can't swear to that. But at any rate, at least on a theoretical basis, you can imagine this sort of thing being true. Of course, in any real situation, there's an infinite number of variables. There's not just a number of rabbits and a number of foxes, and so you would look for a pair of variables maybe that was acting like this, but they would be but there would be external forces from that point of view, which would be other kinds of things like other predators or other sources of food or things like that that are going up and down. And that would be exactly the kind of situation that we're describing, which is you have a flow. There are two dimensions that we care about. There are all the other dimensions in the world which we simply regard as from the exterior. That's the input to our filter, right? And the input to our filter is everything from how much grass there is to how hot it is outdoors. Whatever you want it to be, you just say how it affects the fox and rabbit population. And then you have how the foxes and rabbits affect each other, which is described in this very simple way. And then off you go. You've got a nice. Oh, well, this is a filter because why? Because it's the same thing as this, and this is a filter because we saw it filtering. That's not a good description of why this is a filter. Anyway, it's not a filter really because it's an oscillator. If you did this and if you found some species of rabbits and foxes that reproduced and ate very, very, very quickly, like in millionths of a second, then you'd be able to make an audio oscillator out of your population of rabbits and foxes. And the way you do that, or better yet, if you just took those curves and sped them up sufficiently and then played them out your speaker, then you would hear a tone. Although it would be a dirty tone, right? But it would be right. You get the idea. Okay, so what do we do to get that to happen? Well, it's not so bad. It's this. It's that, in a word, what you want to do is, we know how to make this filter, and we know how to make this filter, and we actually know how to make this filter. All we do is we mess with this gain here, which is the thing that we're multiplying the thing by. Because if that gain is 1, as it is now, the thing goes perfectly in a circle, and if it's less than 1, it spirals in, and if it's more than 1, it spirals out. So why don't we just make that gain be dependent on the radius that we're at? In other words, going back to the picture, when the radius is, suppose this, let's call this radius 1 here, just because we'll just make it be 1. So what we'll want to do is, if the radius is less than 1, we'll want the gain to be bigger than 1. If the radius is greater than 1, we want the gain to be less than 1. And if the radius is exactly 1, we want the gain to be exactly 1. Well, that's easy. All you do is you take the, it's not as easy as I would have wished because we have to get the radius now. And to get the radius, we have a choice. I could either go get that wonderful unit polar object back. Why don't I do that? That would be a good thing. Okay, so let's go find unit polar and copy it in. No. Where did it go? Oh, was it back in 2? Yep. Okay. Unit polar, let's get one. Tilde maybe? Yeah, unit polar is, it's sort of, we'll just not sort of talk too much about what's going on inside, but what it does is out comes the radius and out comes the angle. In other words, what it does is it takes these values. Oh, right. We can do this before we adjust the gain, because the gain is going to be a function of what we do here. So somewhere between the gain, the first thing that we're going to do is we're going to feed this thing into unit polar, and that's going to give us out as outputs the radius and the phase. Right? And then the radius, this number now is the thing which we want to deal with in the following way. If it's 1, we want to get 1 out, and if it's bigger than 1, we want to get less than 1 out, and if it's less than 1, we want to get bigger than 1 out. So a real easy way to do that is to multiply by -1 and add 2. Well, all right, so I'm going to explain now why this makes sense. What I'm going to do now is, well, okay, first off, if 1 comes out, then this is -1, and then this is 2 minus 1, which is 1. But this thing is flipping it around. So if I give it slightly more than 1, this will be slightly less than -1, and this will be slightly less than 1. Okay. Let's see. Now, except, I'm sorry.
If 1 comes out, then, if -1 comes out, then you multiply by -1 to get 1, and then you add 2 to get 3.
Well, -1's never going to come out of here, because this is going to give me
-1.
positive numbers.
Oh, okay.
Yeah, so the smallest this could be is 2. But one thing could go wrong, which is if this thing ever got too big, like if this got to be 3, well, if this got to be 4, then this would be -4, and then this would be multiplied by -2, which would then take the thing and throw it all the way past the origin into the other direction and make it bigger than it was before. And that would be a very unfortunate thing to have happen. So what we should perhaps do is clip it at some reasonable point, like maybe here. Yeah. How about we just oh, caps lock, I hate you. By the way, there's no good reason to have caps lock. Caps lock was a physical thing on mechanical typewriters, and it has no purpose in yeah, right. All right, maybe it has a use. Okay, so I don't need this anymore. Oh wait, I don't want to clip it between 1 and 1. That's stupid. That would be really bad, because it would this would be wrong. That would make it, that would output something. If this was less than 1, it would raise it to 1, and then if it was greater than -1, it would decrease it to -1, and therefore it would always give you -1 out. So this is not good. In fact, what I really want is reasonable numbers between 0, well actually 0. I want, yeah, I don't know, 1/10 and 2. And now I'm going to readjust the thing by that. 2 is a lot of gain to stick inside of feedback, because this happens every sample, so that means after 30 samples it's multiplied by 1 billion. So this is serious gain here that we're offering it. But of course that only happens right around this spot here. And at spots close to the circle it's something more reasonable. Okay. So I think it's probably running, so let's go see what it sounds like. Oscillator. But unlike the oscillator before, let's see, how can I do this? Let's now make this thing be 0. How do I make it be 0? I have to, easy, I just do this. Oh my. Why do we hear anything? I just, is the other thing still on?
Small block size in the other folder.
Oh, is this not that person's patch? All right, I don't have any idea how this is able to make sound. This is like a light bulb that's on without being plugged in.
You severed the connections to the gain control, not the feedback.
Yeah, but this is multiplying now by 0. Unless it's not. It's not because I entered a number in there before, maybe. That was bad. It's because at some point I was throwing messages in there, and then when I disconnected it, recovered the stupid message value. This is a horrible thing about PD that, as you can tell, can get anyone in trouble. All right, good. So now we've truly got zeros in here. I mean, just plain 0. In fact, I'm going to check, but I'm going to check that this thing is truly putting out zeros by saying print tilde and looking at the result like this. Where's the PD window? 0! All right, we've genuinely cleared out this field. This is better than a blackboard eraser. This is really genuinely 0. Okay? Now, the next thing is going to happen is I'm going to reconnect it. And this, therefore, means that it is now in a state where the only possible stable oscillation is unit amplitude. And now I'm going to go back, and some of you see this coming, I think. I'm going to print this out, and it's going to be 0. There is another possible thing that can happen to this filter, which is it can get stuck in the middle. It's unstable. As soon as it moves 10 to the 38th away from the middle, it will then start to spiral out, and within 30 samples, roughly speaking, it will then be it'll then be at the limit cycle. So if I did something, so what I do with this kind of a thing when I'm really doing it is I give myself a little feather to tickle it with, like this. Take noise and multiply it by 1e minus 20, say. Some, very, very small, inaudible quantity of noise. This is 10 to the minus 20th, which is minus 400 dB. You will never hear this sound, right? And then I just add it anywhere that I want to. And just for fun, let's be listening to it. Yeah, we're listening to it. And then the moment I connect this salt, as I call it, nothing happens. Oh, because why is nothing happening? Well, maybe what I'm saying isn't true, but I think it's true. Or maybe, what else could be wrong about this? All right, so I believe there's zeros coming out of here. So there's 2's coming out of here, and we're clipping to 2, but that's fine. We're doubling everything every time around.
Well, that's print tilde.
Yeah, it's time to do some print out. Print. Yeah, there's those little teeny numbers. Either the minus 21, right? Not positive 21. Or are they? Wait. Are there minuses in front of there? Oh, I can look here. Yeah, right. Okay, good. All right, so why is this not growing crazily? I must be doing something wrong. Oh, so let's print what's coming out of here. This will be charming because we're operating at a block size of 1, so we'll get one number for this block, I believe. 2. So why is it that I can multiply this thing by... Oh! This is the delay lines protecting me from getting numerical underflow. They actually refuse to put anything below about this value through. I have to actually raise my signal by, say, 200 decibels up to that value, and all of a sudden, then we're good. And now we have 1s coming out. Okay, what that was protection against the patch driving itself crazy, dealing with 8 to the minus 20 numbers that if you multiply them by each other will make a numerical underflow and cause your computer to slow down by a factor of hundreds, which is a very bad thing to do. What?
Is that denormals problem?
Yes, that's the denormals problem. And every single operation on denormal generates a trap and wakes your kernel up, says, you just multiplied 10 to the minus 20 by 10 to the minus 20, and you're going to get a denormal. And the kernel says, okay, give it to him. But multiplication takes a nanosecond or so, and that operation takes a microsecond or so. So suddenly you've lost a factor of 1,000 in your multiplication efficiency, so you will get very unhappy. Okay. And the good thing to do to avoid this is to use a different architecture besides Intel. All right, sorry, that was a huge digression, but actually an important one, because that's the sort of thing that could get you messed up pretty badly. All right, so this is now the oscillator, and it's not just an oscillator, but it's an oscillator and a filter at the same time. And to show you that, now what I'll do is start pumping it with a nice oscillator. Show you what happens when you filter a sinusoid. By the way, so what kind of a signal do you get out when you filter a sinusoid? Pop quiz. You get a sinusoid. Filters don't change things frequency, they just change amplitude. So sinusoid in, sinusoid out. But that's only true about linear filters. And this is a very nonlinear filter now. It's an oscillator. And it will no longer be the case that when I take this oscillator and put a nice frequency in, I get necessarily anything like that frequency back out. Let's see, I think I need an amplitude control here. I think a linear one will be fine for us for right now. Something like this. I might want to go up to 1,000. We'll see. I don't know yet. Okay, I want that in there. I don't need this, but it's not really doing anything anyway. That was my way of starting the other thing up. Hey, now I don't have key accelerators. Okay. What else do I? Oh, right. And now we're listening to this nice sinusoid. Oh, the other thing. Hey. Oh, I've got my. The gremlins are here again. Oh, I got caps lock. Oh, that's why my key accelerators all failed. Okay, good. I actually have a command to fix that, which I'm going to use right now. Not there, I'm not. That takes my caps lock key and remaps it to something else. All right. Oh, yes, right. And the other thing I was going to try to do was take the output tilde and put one here so that I can listen in on this sinusoid. So there's that pitch for us. And now I'm going to go make myself an oscillator. Oh, whoa, careful. There's an oscillator, and now we turn this output up to see if it's what it's playing. I was not expecting that. It's just playing a distorted version of this. But anyone want to tell me what's going to happen when I turn this thing back down? Give you a hint. At some point, it's going to have well, if I turn it to nothing, it has to go back to its frequency. But now I've got something cool. These are called multiphonics.
So it's like oscillating over.
I don't know how to describe what this is doing.
Well, in terms of the spatial flow diagram, it's crossing back and forth across the...
Oh wait, I'm sorry. Let me get this off so I can so I can stop playing with it. So wait. Oh, I see what you're saying. Maybe is that the thing can't go around zero. Oh, right. So if you took this thing and put something of sufficiently high amplitude into it that it simply pushed it outside of the limit cycle, then you could make it follow your desire. Sort of. Except, it didn't, I'm not sure that's a complete explanation because this is now 1/10, and the limit cycle has amplitude 1. So actually the thing that I'm pumping it with is only 1/10 the amplitude of what was recirculating in the filter, and I already took over the filter completely.
Would the radius,
Oh, hey,
have
why'd that
anything
go
to do
away?
with-
Oh, right, I know. I'm sorry. We're listening to this. Radius. Okay, so what about the... Do I?
Would radius affect frequency or timbre? So if it was crossing that limit cycle as it oscillated, because it's getting pushed, you know, as the gain gets too big, it's overshooting, getting pushed back. So,
Yeah. But I think... Well, we could check. I mean, so what I could do is I could make it do that again. Let's really make it do it. Like 13 seems to be the... well, I don't know. Anyway, we're thoroughly doing it now, right? And now let's see what the magnitudes are that we're looking at here. Oh, I took the print away, which is silly. But I want to be down here anyway. Oh, actually, I want to see what's coming out of this, because that's a measurement of... That's the radius there, right? That's what we want to know. Now I'll get a few of them just to look. Yeah, it's not getting very far off the limit cycle. So how could that possibly be doing what we hear? Well, all I can say is no one understands these things. Although I think I ought to be able to find an explanation for that.
Well, what did you anticipate was going to happen?
Well, I anticipated that exactly that would... I mean, I anticipated that at a sufficiently high amplitude I would force the thing to oscillate at the frequency I was pumping it with. But I thought I was going to have to give an amplitude of 1-ish. And instead I got away with an amplitude of a 10th-ish. So, I don't know. I don't know why I was able to... I don't know why that happened that easily. But the basic thing that happened is exactly what happens. There's nothing else that could happen. At low amplitudes, it has to do this, and at high amplitudes, it has to do that. And so at some point, there's going to be a thing that gets you from the one to the other.
And the noise we're still feeding is too minimal to affect the...
Yeah, that is 200 decibels down. So that's no longer a factor. And here's an interesting thing. My ears are telling me FM, but my brain isn't telling me anything about that. Maybe it's, you could say maybe this is FM because it's perturbing. No, you could say it's both, because it's perturbing a flow which naturally wants to go in a circle, and to the extent that it does it, to the extent that it messes with the angle, it's FM, and to the extent that it, right. And so it's probably doing them both.
Can we say properly?
Yeah, so that's... in fact, it would really be good if I could get rid of... I don't need this stuff anymore, do I? I don't think. I'll go back and get another copy if I do. I just want to make it a little clearer what's going on. I like that impulse generator, so I'm going to keep it around. Let's see, what else should I do? This is just for comparing a sine.
So I suppose you could get other temporal variations if you changed, I don't know what word to use, but the force that would be being pushed towards and away from the limit cycle.
Yes, in other words, if you... So if you put something other than an oscillator in here, then, or something other than a sinusoid in there, then I presume you would be able to do all sorts of other kinds of things.
But I meant like how we're mapping out of unipolar.
Oh,
we have
I see.
We have gains that we're using.
In other words, this thing,
Yeah.
if I change that, yeah, but I don't know if it would change it. Oh, what am I saying? I don't know that it would be really salient how it changed it. In other words, as long as it was sort of working to nudge it into an orbit, then basically, if you nudged it in a slightly less uniform way, then it might be a pretty subtle difference. Might be.
But even if you like increase the amplitude, I guess I'm just thinking of it like AM or something, if you increase the bandwidth of your stuff by increasing how much it gets pushed.
Yeah, but that we can do just as easily up here by.
Yeah.
But a thing which just occurs to me, so this might be another for your own exploration thing. I bet it would be interesting to take, instead of one sinusoid here, take two sinusoids in quadrature, going either in the same direction or in the opposite direction, because you might actually get slightly cleaner sounds out by doing that, because the situation would be more symmetrical. In other words, the thing would be fully rotationally symmetrical if you did that. And that might actually be a good thing to find out about. But I'm not going to,
Which two things are you saying would be fully reversed? You're saying the phase relationship between the two sinusoids?
yeah, between these two, yeah. So pump these two delay lines with a sinusoid again, but make the sinusoid be the cosine and sine of a single phase. Because then what you would have would be fully rotationally symmetrical in some sense. Because right now all we're doing, in one way of thinking, all we're doing in this picture is we're applying forces to the left and to the right, but never to the up and down. So we're doing this, but we could do this, and that would be a simpler motion in some sense, because it would be a pure epicycle. It would be more Greek. Yeah. So that would be worth looking at. The other thing is, well, there's many other things, but try a couple oscillators here, and then they can fight over which one gets it, as well as fighting with it over whether it gets its own frequency or not. Right. So the next matter, the other thing that I was promising you was, what about if the radius changes the frequency? In other words, going back to this picture, perhaps keeping this in place and perhaps not, depending on whether we're doing that trick or not, which we could do or not, I guess, I don't know. Let's for simplicity's sake, why don't I take that out now, so that we're only doing one thing at a time. So going back to this picture, what would happen then if we fixed it so that the rotation had a different speed, or a different angular speed depending on the radius, so that we were making the filter that has the property that its resonant frequency changes depending on how excited it is. Right? Okay, so, and of course it would be, it could be cool to have both of these things going on at once, and, well, we could, so go explore. I mean, this is all just, there's a huge combinatorial collection of possibilities that we could be messing with here. Okay, so, yeah?
The category of what we're doing changed?
We are in a room. Let's see. Let's see, what else is happening?
Are we still working with a resonator, essentially?
Yeah.
Multiphonics resonator?
I don't know how to explain this. We're doing things for which there is no theoretical construct that explains what we're doing, and these are sort of in between the boundaries of things that are oscillators and things that are filters. And people don't name them because they don't understand them. Or maybe they don't name them because, well, we could get into what people are doing when they name things, but that would be a different course. All right, so what's going to happen now is, rather than have a scalar or a control, or rather than have a message that just allows us to set, this rotation, we have to make this rotation itself be dependent upon the angle. Sorry, on the radius, although it could depend on the angle too, and that also I will leave to you to explore, because I don't want to get into there just yet. Okay, so to do that, we have to do something horrible, which is start talking about cosine tilde. Cosine tilde is a computer music cosine, and this is a mathematical cosine. Computer music thinks phase goes from 0 to 1, and mathematics thinks phase goes from 0 to 2 pi. And the cosine function that everyone learns in algebra 1 or 2, I forget, likes its argument to be in radians. And that is the function that ever since the Greeks was called cosine. But cosine tilde is a computer music cosine because that way it runs faster. So in computer music, the whole deal is to get the thing to run fast so you can have 100 voices of this going in real time. Or so that you can run it on your cell phone. So that's all to say that the numbers that we feed this should be smaller by a factor of 2 pi than the numbers that we were feeding these things. It doesn't matter because I'm just mousing my way through it anyway, so this is kind of a little bit academic. And the other thing is, there's no sine tilde because it's computer music. There's actually just a cosine wavetable. And then cosine tilde just gives you access to the wavetable. And if you want sine tilde, you say cosine tilde, and then you use the fact that if you just subtract a quarter cycle and then take cosine, you are doing sine. So here is cosine and sine of whatever we stick in it. And what we're going to stick in it is going to be something which some parameter. We still want this, although the scale is kind of nasty now. So should I rescale this here? I don't know if this is a good idea or not, but I'm going to give myself a reasonable mousing scale. And then we're going to take what comes out of here and multiply it by something that we will determine by just fooling around until we get something nice, which is, how you do music. And I don't know what range of values we're going to want. They might be very small, I'm not sure. Now I'm going to take that and add this constant to it. Or parameter, I should call that. And then I'm going to feed it into these two puppies. Is this what I really want to do? Well, who knows? We'll do it and find out if it's what we want to do or not. Okay, now, I've got to connect this back up the way it needs to be connected, which is cosine. Ooh, did that go in the right inlet? Oh boy, that's the second oldest gotcha in the book. All right, so cosine times cosine minus sine times sine. And then cosine times sine plus sine times cosine. And if you get that wrong, it will either give you silence or an explosion. Okay, so we've got it now. And we're multiplying by 0, so we should be doing nothing different from what we were doing before, I think, now. And oh, right, I never did the save as. So this is going to be 2, and this is, I don't know what that first one should have been named, but this one is going to be the flexitone. Is that how you, I'm not sure how you pronounce flexitone. All right, okay. It's flexitone. Now, let's see, what we're doing is we're putting an oscillator in. Is that what we really want? I don't know. All right, we'll find out. Oh, right, and the other thing I promised you I would do was get rid of this horror show and just, how do I want to do this? I don't want to have that control signal in there, so I'm going to keep the clip tilde around just because it's fun. And I'm going to now make the angle be not that, but number box divided by 100, which is what it had been before. I don't know. Okay, good. So now I'm going to say, let's be almost, actually, let's be really almost critical. And now let's go back and get our impulse generator, which I was thoughtful enough not to get rid of. I'm going to disconnect this. What's coming out of this thing now? Stuff is coming, oh yeah. Oh, you see that? Okay, so let's now, before we test it on our ears, we can test it on the envelope follower. Good, so it's a thing which decays, right? And now we're going to enjoy what it sounds like. Doesn't sound like anything. Oh, because I have to give this a proper frequency, I guess. There it is. And I'm not hearing any flexitone action at all. Oh, why not? Do you remember that I said I was going to leave this at 0 for a moment? Okay, so this is the sensitivity of the angle of, okay, so I'm probably going too fast here, so let me just go back and carefully explain everything that I'm doing now. So I've changed the input. I'm not going to pump it with a sinusoid for now. For simplicity's sake, I'm going to pump it with just an impulse. And that's going to send it out to 1, and then let it do whatever it does when it starts out at 1. But I took out the stuff that forced it to oscillate at 1, and instead am replacing that just with a constant which allows it to spiral very slowly in toward the origin. If this were exactly 1, it would be critically, it would be critical, and critically unstable or critically stable, whatever you say. But this is just barely stable, right? Just barely on the good side of stability. This clip is doing nothing for us right now. And let's see, what else do I have to say? All right, but the thing that's happening now is that the rotation part has now been fixed up so that there's a constant rotation, which I'm fixing with this inlet, and which I control here. Okay. And then we have the radius that we're measuring. We're no longer using it for the gain control, but now what we're going to do is we're going to use it by multiplying it by something and adding that to the rotation. And these numbers on the order of 100th. And this number is on the order of 1 when we do it, so maybe, so what would be a good thing? 1? No, that'll be about 100 times the frequency that's multiplying the resonant frequency by 100, so it should be ultrasonic. Let's just try that first, because that'll be interesting. There it is. All right, so maybe that's a little bit too big. Let's try 0.1. There we go. All right. And now we've got one of those things that we bought in the 70s. No, 80s. Okay. A syndrome, I think they were called.
Syndrome?
Yeah, it's a box with rubber and knobs all the way around it. And you go to a music store and find a syndrome, or get on eBay and look and see. They're probably valuable now. And they sound exactly like this. And you can probably name the disco tunes that thing sounds on. It's very disco. And I thought it was stupid when I first heard it, and now I think it's beautiful. So if you think something is stupid, wait 30 years and you'll think it is beautiful. All right. This is a little bit limited because, well, okay. No, it's not really. The thing is, if we wanted to, well, it's just what it is. All right, now what we have to do is now we should go back and repeat the experiment of driving with an oscillator. But before I do that, I want to make sure everyone understands what's going on here. By the way, this is actually, although that's the syndrome sound, this is not really what the syndrome was. It had a voltage control oscillator in it and an envelope generator. And this is incorporating all that into the oscillator effectively. so it's somewhat different. Yeah.
What about if you put it critically stable?
If I did what?
If you made the
Oh, if I made it, what would happen? Well, let's find out. The only thing is I don't think I should put an impulse in anymore if I do that. I think I should put in something gentler. But we can do it. Okay, so I'm going to say 100. I'm going to turn this down a little bit because I'm not dead sure what's going to happen now. And I guess let's put in a little noise. I think I know what's going to happen, but I want it to be a surprise, so I'm not going to say. And anyway, I'm probably going to be wrong, and I don't want to get embarrassed. So let's get our little noise pumping operation here. Yeah, there it is. Ouch. Double ouch. All right, this is not what I thought was going to happen. All right, I don't know why that's doing that. Not against it, but... Someone found a way to describe what this sounds like.
Those dentist tools.
Oh, yeah. That would be one. Yeah. Okay. Okay, well, I don't know why this is happening. Oh, I do. So here's a possible explanation of what's going on. The noise is kicking it, is sometimes increasing the radius and sometimes decreasing the radius. And when it decreases the radius, this inner stuff goes slower, so it drops pitch. And when it increases the radius, it goes up. But the only thing, normally you would expect it to go out and you gradually get bigger and bigger and bigger in the aggregate. But what's preventing that is that it's getting clipped at 10 units. There's still a clip in here, which is the only reason I was willing to do this at all. It was because I had that. So that's what keeps it from getting past whatever that top frequency is. Actually, it's getting well up above my hearing already. All right. So that's that. And in fact, that would suggest that if I just made this barely stable, we would get this kind of thing. All right. So now it's a filter which, the more you pump it, the higher it goes. All right.
Can you go back to the flows again? Can you say that one more time?
The which? Oh, I see. The flow, yeah, this picture here. Okay, so we're now in, actually, we're in this situation now, the flow that is stable, although we tried this one and this one. But what we have done to the thing is we fixed it so that the flow goes at different angular velocities depending on the radius.
So we pump noise in, is it every frequency?
Yeah. But and in fact, if you stop pumping the noise in, it would just, whatever radius it was at, it would just keep it that, except it would probably drift slightly because of numerical error. But basically what should be happening is, if I make this critical again, yeah, good. Now we've got this stuff going, but we don't have noise yet. If I stop the noise, then whatever radius it was at is where it's going to be. And so on. So it's a roulette wheel of some sort.
Highlight the small bulk size window.
Yeah.
So we're taking the radius, we're
There.
attenuating it by arbitrary factor.
Yeah.
And adding the offset, which is our rotation.
Yeah, so that's a base rotation rate. I wonder if we even need that now. Because, do it?
I don't know.
Yeah. Oh, we could even do something worse. We could give it a negative rotation rate so that there would actually be a radius at which it had zero frequency. It would just be parked. but then when it got out, it would go one way, and when it went in, it would go the other. Right? Why not? Let's see, now, should I do that with no, I should do that with it stable. So just to check this out, so now we have this. Oops, give me some sound. And it should be the case that as I turn this down very low, we get closer and closer to the nominal frequency, which is this thing we're controlling here. Oops, sorry. Right? So now what we're doing is, I just made the thing very quiet so that it never gets very far out from the origin, so it's basically only this frequency and not getting any extra frequency to speak of from the radius. Right? And my purpose to doing that was to make this frequency negative. You can't hear, you can't hear an appreciable difference because now all that's doing is instead of going around counterclockwise, it's going around clockwise. But now, when I push it, it will start going less and less clockwise until it stalls and then starts going counterclockwise. So it gets slower and slower. I can't explain why you hear that crackling. That's just another thing for further exploration, I guess. Right. So the other thing to do is pump this with a sinusoid, as before, right? So pump it with sinusoid. Here, the situation should be, oh, I got a didgeridoo now. Okay, right, so again, it's, what am I saying? It seems always to be the case that we're controlling the frequency of the oscillation from here. Why would that be? Oh, right. Because we're in a regime where it's almost linear. So what we need to do to make it not, to give us frequencies other than what the oscillator is push it hard enough so that it starts acting nonlinearly. And the further out we push it, the more it's going to hate the frequency that we gave it. And actually, I should give this 0 now. No, I should give this a small positive number. So there's oscillator. Oh no, there's no oscillation there because I turned it off. There's what the sound is, and then if I listen to what happens when we use it. That periodicity that you hear, that is the, what am I saying? That's the, no, it's not. I don't know how to explain that. I thought I was going to be able to tell you that's the number of times the thing, that's the number of times the forcing oscillator turns around per cycle of the big oscillator, but the thing is the fundamental frequency we hear is that of the forcing oscillator. So that's not the correct explanation. It's maybe that turned, what I said turned inside out somehow. So the thing that I did not expect was that this thing didn't have a strong enough opinion about the frequency to force this thing into a different frequency. That's what that is.
Could we give a broad stroke overview of the architecture that we have here in general, including, well, mainly the small block size?
Yeah, okay. Okay. Actually, to be simple, actually, everything's happening in here because this is just what we're pumping it with, and all we're really doing is listening to the output in various ways. So, right. So basically, the way I think of it, the order in which I think of this is, the thing is framed by the fact that there's a feedback network with two numbers getting fed back, and there's simple numbers because this is a block size of 1 and I asked for a delay size of 0, so it's giving me a delay of 1 sample. So basically every sample we read these two values, do stuff, and then write those values back. And what we're doing, let's see how to say this. What we're doing fundamentally is that we are adjusting the amplitude and then we're rotating. So this does nothing but change the radius and leaves the angle fixed. This does nothing but change the angle and leave the radius fixed. Well, right, and the mouse doesn't show up on the recording, so by that I mean that stuff changes the radius, this stuff changes the angle. So how do you change, so what do I change the angle by? What do I change, okay, what do I change the radius by? Well, I change the radius by multiplying it by 99%. And what do I change the angle by? I change the angle by adding an angle, or by rotating the thing by an angle, which is, first off, I just give it a fixed angle. And second, I give it a variable angle, which varies proportionally to the radius. So this is measuring the radius of these two things considered as a point on a plane. And that really should have had a comment. Yeah. So what that does in the flow picture is that fixes it so that the rotation is by a bigger angle when we're on this circle than it is when we're on that circle. Except that, so the next thing, essentially, well, okay, so there, as promised today, there are two basic families of nonlinear filters that are sort of the first things to try. One is the forced, or whatever you say, the rabbits and foxes thing. I should find out what it's supposed to be called. It might be called the forced oscillator in this context, but it might not. And the other one is Slew. I think they're called Slew Generators, anyway, it's called slewing. And to make a thing slew is to enforce a maximum rate at which the thing can decrease or increase. And this is a great deal less poetic than something that sits there and oscillates unstably, but is actually terribly useful. And so warrants looking at. Yeah? Or,
it's just looking at slew limiting, isn't it?
Might be, yeah, that could be a way of saying it. And then, yeah, when you buy an op amp, there might be a slew rate, and so on like that. People used to say that the reason tube amps sound warm is because they slew instead of following their inputs instantly the way transistors tend to. Except then they said, no, actually the reason is because tubes clip softly and transistors clip hard. Tubes clip as hard as you please. They they just corner when they clip. And there might actually be some slew action in tube amps, but I actually don't know why tube amps sound nice and transistor amps sound like transistor amps, except that there might actually just be some way we've trained ourselves to think that transistor sound is cheap and the tube sound is expensive. I don't know. And for that you can read Thorstein Veblen's wonderful book, The Theory of the Leisure Class, by which he proves that anything that is expensive is virtuous, in his words. All right. And he says, of course, I didn't mean anything deprecatory about that. I'm just stating the thing as I see it. I'm just speaking as an economist. Anyway, So to make a slew generator is going to be easy enough, but then to sort of get into what it does, or slew generator, whatever you say, slew limiter or something like that, is not going to be terribly hard, but then the things that it will do will be interesting. In particular, it's the thing that people always use when they want to make a dynamic range processor, the compressor, limiter, noise gate, whatnot. People always seem to use slew limiters as the thing that makes their envelope follower work in those devices for what might be very good reasons, or might not, I'm not sure. Okay, so first off, how do you do it? Well, the way you do it is you start with actually, conceptually the way you could do it is start with a low-pass filter, although the thing won't really be exactly a low-pass filter when we get done with it. But low-pass filter to start with. So the first thing that we do in order to get a nice low-pass filter going, I'm going to want that. We get rid of TED 2, and we just have TED 1. And since we only have one dimension now, there's no rotating, and there's only amplitude changing. And this radius is the wrong word now. This is something like recirculation or feedback. Yeah, except everything's feedback, so that's a bad name to give it. And I guess we don't really need the noise salting it. All right, so something like this. And the other thing that we discovered you want to do is for it to be a proper low-pass filter with the appropriate gain, is you should multiply it somewhere, and I think I'm going to do this at the input now. You should multiply it by, is that a good idea? Yes. Okay, I'm going to do this two ways. First I'm going to do it the clean way. I'm going to multiply it now by a thing which is 1 minus this, which is to say, what's the best way to do this? But I really do want to keep this stable now, so I'm going to clip it between 0 and 1. I'm just going to do it as a control operation. So there's going to be there's going to be a feedback gain, which we multiply by that, and then we're going to take 1 minus it and multiply that by the input, and then add them. My reason for expressing it this way is because it's conceptually clean. What we're talking about here is a weighted average between the new sample and what was coming before, which is weighted 99% the past and 1% the present. And now there are things to do. None of this is of use at all, although maybe I'll want to print tilde at some point in the future. Oh, and the inlet now might as well talk to the feedback recirculation. I don't know. I'm not sure we even want that. Oh, hey, go away. Save. All right, and now what we've got is a thing which we can listen to, and it does. Well, actually, I got this going before, so you know what it sounds like. Well, you put an oscillator in, and you actually get an oscillator out. But the oscillator out is attenuated depending on the frequency. So now it's 97 going in and 78 going out, and if I drop this, it will get louder. So it's a low-pass filter. Everything is cool. Other thing about this is what's the impulse response. I can't remember if I even showed you the impulse response in the graph before, but I'll do it now just for giggles. So let's go make an array. Sorry, put array, and I don't know how many points I want, probably 500. I'll do all that, and it'll be good. And then, there you go. No, I don't want to do that. And maybe I want it, I don't need this anymore, but I want this to have slightly better dimensions. Yeah, okay, and then, oh, that's okay. And that's not a sinusoid for comparison, that's bullshit. All right, and then we have to have a tab right tilde, array 1, with a button. And now what's coming out of the filter? Nothing. which is appropriate because we're not putting anything in. And what comes out of the filter if we throw in an impulse? Not a whole lot. Let's do that again in a better way. All right, so what I'm going to do is I'm going to multiply it by 100 and graph it. Now let's try it. Yeah, here it is. Okay, we all know. Okay, this 100 is a good value to have chosen because inside the sub-window I multiplied this by 1/100th. And so I just corrected it to have a value of 1 on the first sample. But really this value is 1/100th because that's what came in. And then each value after that is 99% of the previous value, so it is a falling exponential. Okay? And then if you put a sinusoid in, no, sorry. I don't know. Then you get a sinusoid out. Oh, kind of big one because I'm multiplying by 100 still. Yeah, sinusoid in, sinusoid out. All right, now, all right, faster sinusoid, lower amplitude, but faster sinusoid out. Okay, now what a slew generator or a slew limiter does is instead of allowing the thing to be its own sinusoid, let me back that up. I'm sorry, I need to explain something else about that. Let's go back to the impulse. Okay, so now you could say, well, this is cool, but I want something that just goes down in a straight line and then hits 0. Why would I want that? Well, for instance, this might be an amplitude envelope, and I might want the thing to shut up after a fixed amount of time, or this might be a pitch envelope. In fact, this might be I might have put a step function in to change a pitch from one thing to another, and I want the pitch to slide instead of to just jump. But I sure don't want to make that slide by being an exponential, because it will just sound hideous. I mean, this is a bad gliss. Okay, so let's make a gliss for you. Let's see, you need an oscillator like this. Don't need the multiplier even. And now I'm going to put numbers into the low-pass filter and play them as frequencies out here. All right, so here I'm going to just put myself a number box and say 440. And nothing. There should be 440 coming out of here. There's 0 coming out of there. Oh, yeah, I need to make a signal out of this. It doesn't have to do this very often, but every once in a while you really have to promote something to signal. And now I have to retype 440 because I didn't know it was there. And 120 dB is coming out of here. That's nice and loud. Well, that's what it is. Why is it 120 dB? Oh, yeah. The number 440 is coming out of here, which is a loud, which is a lot. It's 440 volts, which is too much to put into your VCO. But since we're being now, why do I still hear nothing? That's the next question. Got all this stuff coming out. I'm putting it into the oscillator. And if I graph it, yeah. All right, so I still don't, okay, right, and I was just in the middle of adding a print tilde to this thing. By the way, you should always save everything every second or two. I actually still had that print tilde I was telling you I was going to try to go into to do this and get nothing because, yeah, there we are. I think 0's out. I was going to put a signal in here. Oh, this is, yeah, so what's going on? I was going to say 440 and put that into a signal tilde. I got 120 dB and I've got values of 10. That is 120 dB. Oh, what about that clip tilde? Duh. All right, so I was playing 10 hertz and then wondering why nobody could hear it. What's a good thing to do here? Should we get rid of it? No, we should actually just... we're not going to protect our ears anymore, but we're at least going to protect our denormals. And now we're getting good numbers there, and maybe we've got something audible now. Yeah, 440. There's nothing like taking an unscheduled break to debug something. Oh, listening to 440 volts, that's no good. Thank you. Yes, I want I want that OSC tilde I think I might have had before. Or maybe I never even put it on there, I don't know. Hey, come here. Sound, right? And now the deal is when I change this frequency, well, all right. Thing there is that 99, oh, I got to make the array again. Sorry, turn this off. 99%, which means a drop off of essentially 100 samples, is very short period of time. 100 samples is 1/440th of a second. So what you're hearing here is a glissando that lasts 1/440th of a second, which, so unsurprisingly, is not terribly perceptible. So now what we do is we say, that means we should, to make a nice 1 second one, we should make this thing 44,099 over 44,100. In other words, 1 minus 1 over sample rate, so that it takes sample rate number of samples for it to drop off, and then it'll be a thing of, then it'll be a 1, or sorry, then it'll be 1 second. So that's about 99.995, I believe. No, if I multiply that by 20,000, I'll get 1. So it's actually this number. That's about 1 minus 1 over the sample rate. Ridiculous number. Oh, I should probably have specified this number instead of this number. Right? Because then the lower the number is, the lower the frequency cutoff of the low-pass filter. Anyway, I'll leave it this way for now. And now we give it 220. Well, sorry, 220. And it just sucks. Never makes it, and that's really annoying. It's especially annoying if you're going down. Like, all right, sucks. Okay, so what we need is something that doesn't do the exponential, it does a straight line. And to do that, okay, so maybe what I should do now is I should make there be 2 filters. Oh, I can just have them live in the same place. Maybe this is going to be good, and maybe this is going to be horrible, I don't know. I'm going to make another one. It's going to use TED 2 because it's in the same patch as somebody else is using TED 1. All right. And this one is going to still be my nice low-pass filter for comparison's sake, and this is now going to be a slew generator, or a slew filter. But actually, before I do that, I am going to fix it so that this thing is backwards. So I'm going to put this one here, this one here. Hey, no, not there. Here. And furthermore, I'm going to take this number and multiply it by the sample rate. No, divide it by the sample rate. So that it is the response speed in Hertz. I'm going to give it 1, and then I'm going to check and see if that actually does the same thing. About the same, anyway. Okay, good. Okay, now if I make this thing be 10, then it does the same deal in 1/10 of a second. Hello, come here. Right? Which is still bad. It's not quite as bothersome now, but it's not a slew, it's an exponential. Okay, now I'm going to shut this thing up while I work. All right, so now what I'll do with the same number is over here, actually this same number, this per whatever, per sample, is going to be to make a thing which takes the input and takes the output and compares them and moves the input in the direction of the output except only as fast as the slew rate allows. So to do that, first, all right, so this goes away. So to do that, first what we do, let's see, we'll use the same input. This might be a little, all right, I don't know how to do this and make it clean. Like that. All right, so now we're going to take this inlet and we're going to subtract the thing that we had out previously. And that is going to be the number of units that I would have to add to the recirculating amount to make it equal the amount that's going in. So now if I'm in a mood for accomplishing nothing whatsoever, I would say, so just take the previous value and then add what I have to add to it to make it the new value. And now this is vacuous. What I'm doing is I'm taking the input and I'm subtracting the recirculating value from it. And that gives me an increment, which I'll add to the recirculating value, and that gives me the input. So this is now the filter, which is called the identity. It puts out exactly what went in. And I'm going to just check that because even at that level, you could be wrong. So I'm going to make another oscillator for listening to this. Yep, seems to work. Oh, sorry. Right? Instantaneous change in frequency. Okay. Now, instead of using this value, what we'll do in order to make a slew generator is we'll simply clip that value so that it doesn't exceed a certain amount. So that's the amount that this is the amount that we would have to add to get all the way to where the previous value, to where the input is. But we will only go as far in the direction of the input as we are allowed to by the slew rate that we are going to specify. So to do that, all we need is a clip tilde object. And the clip tilde object is going to be from minus something to positive something, and that minus something and positive something is going to be exactly this number. So I'll take that number and multiply it by -1. I don't know if I want to clip it or not. Sorry. That'll be the lowest, just times, not without the tilde. And then give it the actual value as a maximum positive value. And then do this. And now, since I just made some message connections, I have to retype this number. Anyway, I want 1 and not 10. Okay, and now, what comes out here? Let's see, are we still doing it? No. But here, what? I think I got the number wrong. It's slewing, but it seems to be taking a minute or two to get up there. So what should oh, right. Yeah, this is the thing I forgot to tell you. The thing about the slew generator is you don't specify how long it's going to take to get to its destination. You specify how fast it gets there, but I asked it to change its value by 770 volts because it was at 110 and I asked it to go up to 880. And so what I really wanted to do is change those 770 units in this amount of time. So so it's going to take 770 seconds if I wait for it this way, but I'm not going to do that. For right now, I'm just going to multiply by the range of interest, which is 880 actually. And this is, all right, so now there are things that you could complain about here. I'm going to retype the 1, and now let's see how it does this. Save that. What have we got? 110 and 80. Slewing. And I think you'll agree that that sounds a lot nicer now, at least now that I've been prepping you to believe it does, than this. Right. Even though the rate was the same at the outset, the thing kept on slowing down, slowing down, slowing down, instead of just getting to the point when it was there. All right. Questions about this? Okay, so this is the thing that I hit, by the way, without realizing it. It shows you what the horrible thing about the slew rate limiter is that you have to know the scale of the input that you're going to be operating on for the thing to operate in the way that you want. In other words, if you double the input of something and feed it to a slew limiter, you'd better double the possible slew rate too if you want it to do the same thing. Right? Maybe you don't, but if you do, or to put it another way, you have to actually think about the range of magnitudes that the input's going to have. You have to have the signal to be within a reasonable range of magnitudes for the slew rate limit that you have chosen. Is that clear? So for instance, if I took this same thing and I started applying it to amplitudes, which might be between 0 and 1, then all of a sudden I would find that everything was working 800 times faster because I'm working on a scale that's 800 times smaller. And, well, all right, it sounds like it's an easy thing just to, you know what kind of range your signal is going to have. And you do when you're making patches for yourself, but when you're making patches for someone else, you don't. And then, or if you're going back to a patch years later and trying to reuse it, you might not know what range it was that you thought it was and so like that. So it actually is kind of, it can be noisome to have to know what the range of, what the range of your input is. That said, there are large classes of applications that simply do have to know the range of the order of magnitude range of the input, like fuzz pedals, which clip and which and the clipping range has to be something like the range of output of your guitar for the thing to clip appropriately. So this, along with say clipping as one possible kind of distortion, is a thing which is range sensitive. Will work at certain ranges and not at others, or do different things at different ranges. Okay. Now, having said that, let's see. The next thing to do is to apply our slew limiter to audio waveforms to show you how the audio waveforms change when one starts applying slew generators to them. Actually, so there are really going to be two applications of interest here. One is that, and one is the compressor limiter. And well, I'll just do those one at a time. So first off, the slew limiter as a the slew limiter as a waveform modifier. I guess I'm going to call it that. Well, so now what we're going to do is rather than make glissandi for us, which actually was interesting, but only what it was and nothing more. I'm going to start feeding it start feeding it sinusoids and then see what I can get the thing to do for us. Recirculate. Okay, so now what am I going to call this thing really? Okay, so now the range of the thing is going to be 1 because I'm going to be dealing with audio range-ish signals. Gee, this should be presumed. Range is not quite the right word, but I'll call it range anyway because of range of input. And that could be a control. I don't have to bake this into the patch, but I'm going to bake it in for right now because, well, this is going to now be the. This is in hertz. This is speed. Or a way that you can slew rate, or to say it another way, if that number is 10, and if I give a step of a volt, it'll take 1/10 of a second. If it's 100, it'll be 100th of a second. If it's 1, it'll be 1 second. So this is the inverse of the slew time, or it is the slew rate. Slew rate. Maximum slew rate, goddammit. Limit. The slew limit is what it really is. Because this is a slew limiter, and my eye is sick. And my brain is going fast too. Alright, here we go. Okay. Good. And now I'm going to make the slew limit be something, I don't know, 100 hertz-ish. Because I'm going to pump it with audio frequency sinusoids. And then I'm going to start graphing the output, so it's too bad I lost my array. 500 of these, please. Array 1, good. Put it down here. I'm not sure how big I want it, so I'll just leave it. And tab right, array 1. Bang, hey, no. That's better. And I'm going to start looking at the output. First off, okay, give it a frequency. And listen to it and see if it's doing anything at all. Oh, this is the low-pass filter, though. And anyway, it's not doing anything. Oh, right, there's no amplitude. Still nothing. I see stuff. What am I doing wrong? Oh, that's tiny. Oh, right. I don't want to oscillate at this frequency. That's no longer what I'm trying to do. Just trying to listen to the waveform now. There it is. Okay. All right, we've got it back. We have a nice sinusoid coming out. This is the low-pass sinusoid. And here now is the slew limited sinusoid. And here's what it looks like. Well, all right, let me drop the frequency of this sinusoid. Let's drop it some more. Oh no, let's drop it some more. Maybe I'm not doing what I think I'm doing. Just making triangle waves. Well, the thing is, maybe this limit is too low. Oh, wow, there it is. It's changing something, and what it's changing is this. As soon as I get it... All right, here's what I want. Except let's now give it a higher frequency again. So we can see a cycle. And now I'll push the slew limit up. Now I'm going to drop this so we can talk about what we got here. This is good. All right. This is what I want you to see. Okay, so what's happening is it follows the sinusoid for a certain portion of the period. And if I drop the amplitude of the sinusoid, say, if I drop the amplitude of the sinusoid, there's less slewing because the slopes are smaller. But as soon as the slope of the sinusoid climbs up to the point where it exceeds the slew limit here in volts per second, then the thing just becomes a straight line segment until finally the sinusoid slows down to the point that this line segment can catch up to it. And that is amplitude dependent, because increasing the amplitude of the thing increases the slopes here, and therefore increases the amount of time, or the fraction of the period during which the thing will slew. All right? Okay, questions about this? Yeah.
Is there a proportion between the amplitude and the frequency? Like if you decrease the frequency or increase the, or
yeah, exactly. So to answer that question, I could say this: the maximum slope of a sinusoid is 2 pi times the amplitude times the frequency. In other words, the frequency goes up, the maximum slope goes up, and the amplitude goes up, the maximum slope goes up too, and they're both proportional. So if you want the maximum slope to be fixed, if you're increasing the frequency, you should proportionally decrease the amplitude. So the loudest sinusoid you can get through this thing is smaller and smaller, depending on how, as the frequency gets higher and higher. Would be one way of saying it. And in fact, I believe it's the case that if I whatever this waveform is, if I now doubled the frequency and halved the amplitude, I would have the same waveform back again. Because everything would be, well, let's just check it out. So I'm going to half this, 26, and I'm going to double this, 220. And now when I snapshot it, we should see the same thing, half as big, but twice as many cycles. Right? For what that's worth. It's a thing. One thing that you could want, and you could certainly want this, is you could not like the fact that you only got odd harmonics out of this thing because it has the odd harmonic symmetry still. Yeah, because going up, it got the same treatment as it got going back down in the other half of the cycle. And no matter what you set the slew rate to, that's going to be the same, right? And that was a thing which was controlled when we were clipping stuff to mess with its timbre or mess with the waveform. The way to deal with that was to add bias, as they call it in the amps, right? You just add something to the thing before you throw it at the clipping function. If the clipping function is odd, and that will make it not be odd anymore, and then you won't get, then you could even as well as odd harmonics out. Here, what you do is you ask for the slew rate you ask for there to be two slew limits, one on the way up and one on the way down. All right. This is done ubiquitously in the trade, so it's worth having this possibility. So to do that, we'll make one of these, and then I'll just make another one, and I'll give myself a single control to control them both, but then I'll be able to adjust them afterward. This is a bit sloppy because I should probably think about the implications of, well, you can see why this is sloppy. So this is going to be I guess we're going to multiply twice by the presumed range of input. But on one of them, we're going to one of them is going to be on the way down. Let's see, I'm going to call this one down and this one up. And then should up or down go first? I don't know. Okay, and so up is going to be this maximum that we put here. And, why didn't that connect? Because I just missed it. And down is going to be, still, that's as it should have been. All right, and now we give it a slew rate. And now, if I've done this right, we haven't changed anything yet. Yeah, good. And it sounds like this. Still odd harmonics. Yeah, it went up an octave because of the stuff I did there. And now I'm going to make the slew limit up be fast and the slew limit down be slow. And then we're going to get this. Sorry. Okay. So now we have the base, a digital wannabe Sawtooth generator. The Sawtooth is the worst signal to operate on digitally because it's not the worst, but it's as bad. It's bad enough that it could be the worst because of its band limiting uglinesses. This is a sort of a way of getting a sort of approximate Sawtooth that at least has a sort of, basically it won't jump because it can only slew, but we can fix it so that it's allowed to almost jump, and then it can do stuff like that. So this is one possible way of taking a sinusoid and getting a Sawtooth out of it. I'm not dead sure, but I think there might be some analog oscillator modules that basically do this to make their Sawtooth thing by having a sinusoid and then doing the slew thing. Although usually they go in reverse. They usually get their sinusoids out of their Sawtooth generators, I think. By the way, never mind. Sawtooth generators are quite a puzzle in digital land. It seems to be easy to make a Sawtooth generator in analog oscillators, and all the things that analog oscillators do to make Sawtooth things are very hard to capture digitally, and usually you have to do things that are fundamentally quite different to make the digital versions work. But That's probably for some other seminar, some other time. Okay, so this is the Slew Generator as a waveform messer-abouter. And once more, it's interesting that you get out timbres that are highly dependent on what you put in, but different in a way that is quite different from the way clipping sounds. Now, if you wanted to now, you could make, or you could think about making something that slewed and clipped in a way that, say, a tube amp stage might. But I don't personally understand enough about how tube amps work to be able to tell you exactly how to do that. You would have to go find some tube amp expert and ask them how to do it, and then go back and make your nonlinear filter actually do the tube thing. But the tube thing then would have something like this slewing going on, which is a feedback mechanism, but also something like clipping going on. And then you perhaps would be able to get things that you would put sinusoids in and would get reasonable, warm, beautiful tube fuzz out of. Problems with this. Maybe it's not obvious that this is a problem, but it's a bit all or nothing, this slew business. And what you would really like, although I've never been able to put my finger on what this is, and this will come back up in the context of doing dynamics processing, by the way. What you'd really like is a slew generator that slews at different rates depending on how far it's got to go and or, well, essentially that. In other words, what if rather than it can move up to a certain speed, but then it just limits hard at that speed? What if you made something that would follow the signal never quite exactly, but would go at 99% of the way to the next sample at low amplitudes and only would go 50% of the way up to the next sample at higher amplitudes or something like that? In other words, so then you would get something that would have some sort of stiffness to it. It would, maybe stiffness is the wrong word. It's elasticity, but yeah. I don't know how to explain it. So at any rate, I've thought for hours about what would be a good general design that would allow you to make things that whose slew rate itself, whose slew limit actually depended on the amount it had to slew to, but was still limiting in some sense. But I've never been able to put a good conceptual framework around that in such a way that I could build one of those things. But if one could build one of those things, then when you put the sinusoid to it, you wouldn't get these moments when it stopped slewing and started following, these bumps. This is actually, I believe, a discontinuous change in slope that it hits here, because the sinusoid was going up, the slew was going down, and the twain crossed, and then suddenly the thing was going in a different direction from where it was going before. And that creates, 1 over n squared harmonic stuff, which, you could want, but you could want to limit, because that could be not sufficiently band limited for whatever you were trying to do. And if you had something that actually made some kind of soft transition between trying to chase this thing on the way down and chasing it on the way up, then you would have a slew generator of a sort that had rounded corners in it, which seems to me like it would be an excellent thing to be able to order up. And in terms of sound, the thing that you would be able to avoid is this buzziness. There's some buzz in there, some high frequency buzz, and that, I believe, is you're listening to these things here, and they will cause little amounts of foldover, although they'll cause substantial amounts of foldover if you actually push the frequency of this thing up quite high in the kilohertz or tens of kilohertz even. Then you'll just be listening to lots of foldover. And it would be good to have a softer way of doing this that limited that. But, yeah, that's a problem of definition that I don't really know how to solve right now. And that comes up in the next application, which I want to show you, which is the which is the dynamics processor. The thing that, okay, so the reason that we're going to want this for a dynamics processor is the following. What a dynamics processor does is okay, so dynamics processors include limiters, noise gates, and companders, which are compressor expanders. And what they do, roughly speaking, is they react to changes in level of a signal and apply an additional gain, either to make the change in level smaller than it would have been or larger than it would have been. The most frequent use of this is a so-called limiter, where you have something with a large dynamic range, like a singer, for instance. And the singer is by and large going to do something reasonable, and it's going to blow out your, whatever it is, 70 decibels of audio, so you map that to 20 dB below your headroom, and then you're cool until she hits 90 dB, which is, loud. But then she lunges at the microphone, and suddenly it's 100 dB, and you're clipping. This happens. And it happens in performances when it wasn't happening in rehearsal too. So it's the sort of thing that's not the moment where you want the equipment to fail. It's probably an important moment in the piece to boot. Either that or, well, anyway. So what you would like to do is you would like to let her through at 70 dB, let her through all the way to 90 dB, but before the equipment clips or does something even worse than that, catches on fire, you want to drop the gain quickly so that the thing doesn't actually clip, but is turned down to a safe level so that she can hit the 100 dB and still come out at 90 dB and look like she's coming out at 100 dB, so you'll still hear the 100 dB because you've got because you see the spectacle, right? Okay, this is first-hand experience speaking. This is not theoretical at all. And percussion, same deal. Percussion even more so in some respects. Well, other things happen. A thing about percussion that's even dicier than singers is that not only do things sometimes get louder than you expected, but when they do so, they can do so in 1/10,000th of a second, because all it takes is a really good whack on a place that's close to the microphone, or actually just whack the microphone itself if you want, and suddenly the signal just jumps in 10 samples from nothing to over the top. So for a limiter, you actually are very interested in being able to do this asymmetrical slewing thing. The situation there might be something like this. You have a level that's going up and down, cool. And you want now to measure the level. Yeah, you want a way of measuring the level. So how do you measure the level? Well, you just slew toward the next sample. If the next sample is quieter, then you slew down. If the next sample is louder, then you slew up. And that becomes a low-pass filter like this. Okay, so this is not a good example because the slewing is so fast that the measured level is actually going up and down during the life of the sinusoid. So this is not a slew generator acting as an envelope follower at all. If you want a slew generator to operate as an envelope follower, let's do this in a different window. So we'll save it as, and now it's going to be 5, and we're going to work toward a compander, although I don't know how far we're going to get. Okay, good. All right. So, all right. First off, loudness of the signal. How do you measure that? Well, the first thing you got to do is square the signal. What that does is that gives you the instantaneous power of the samples that's coming out. Oh, and we're going to put this. So we're talking about this signal here. So I'm going to take the signal and square it, and we all know what that does. That raises it by an octave. And the top value will be the square of what it had been before. There it is. Oh, cool. There's the thing. So 0 is down here. And so what we've got now is, let's see. To show you what it looks like, I'll make the slew limit be obscenely high so that you'll see the original waveform. This is the square of the sinusoid was half this frequency and going positive and negative, and now it's the square, which is between here and here. Now we'll low pass it out the wazoo until we get a steady result, and that will be the envelope follower output. That'll be our estimate of the amplitude of the sinusoid. And of course we could do that with a low pass filter, and in fact that's what that's the simplest way to do it. But the what's the right word? The way the industry has almost universally decided this should be done is by using a slew limiter instead. And I don't know what kind of limit to give it, so let's try that. Okay, and there's an estimate of how loud the thing is. And of course, when the thing, when the sinusoid moves towards 0, we start concluding it's less loud, but then it starts moving away from 0, and then we start concluding it's louder again. And this is kind of, okay, maybe this is a little bit too fast for this particular thing, so let's talk 50. And there's, you know, sort of an envelope generator, or sort of an envelope follower, I guess I should say. And now, let's make an extreme compander. The extreme compander is going to take whatever comes in and is going to adjust it so that the output is unity gain. You should never do this. In fact, I'm going to show you why you should never do this. Ideally I should do this with a real sound, but I guess I'm not right now for just practical reasons. Okay. So we're showing that now. So this is an envelope follower output, and now we're just going to take and go away. Oh, we don't need this. I don't know if we need this. Wow, we've been carrying all this stuff around and we haven't needed it at all. Okay. This might be useful here someday. All right, so we just take this and we just divide the original signal by it. Oh, that's not good because this is in units of the square of the original signal, so we need to take a square root. Let's see how this does. First off, what does that look like? It should look roughly the same, except the overall level should be different because it's the square root now. And this now is sort of the RMS amplitude, root mean square amplitude of this signal that we're putting in. Okay, and now we'll just divide the thing by its own RMS amplitude. Oh, no, wait. And now we have a signal which is a sinusoid, except it's not, but anyway, I now can change the amplitude here. And within reason, nothing changes. Okay, so now it's nice and loud and the measured envelope is way up here. Now I drop it. Measured envelope is there. But since I'm dividing by that, nothing's changing. Except, actually I'm dividing by a thing which isn't perfectly constant. So in dividing the thing by that, and that's especially evident when I drop this more, what's happening now is, here's the measured envelope, and so I'm actually changing the waveform of the thing by dividing this thing out. Well, no problem. We just take the slew limit and make it such a ridiculous value that the thing is basically, for our purposes, pretty much constant. And now I can change my amplitude all I want. Now you hear it changes in amplitude because now what's happening is this is so slow that the thing takes a moment to catch up to my changes. So it'll actually dip in amplitude and then recover. And then when I push it up, it'll jump out of this and then recover back downward. But then if it changes gently, I don't get any change in amplitude. So this is a volume knob remover. Now, that's not actually a responsible thing to tell you, because that was cool for a sinusoid. That worked kind of, I mean, not perfectly, because even though this is almost flat, it's not so flat that you wouldn't hear it if you were, if you were going out and looking for it, you would actually hear the harmonic distortion that this was causing still. But everything in analog puts a little harmonic distortion into your scene, so we can just call this analog sounding. Right? Okay, so but the thing is, now there's a bit of a thing, because now the drummer whacks the drum too loud, and the thing takes 1/6 of a second to respond, and so you've already lost your speakers and your audience's eardrums before the limiter kicked into this limiting thing. So you want the limiting to be fast, maybe. Well, what sound engineers do is they make they use the fact that the slew limit can be different on the way down as on the way up. So now going back to here, again, if I take the slew limit and make it something reasonable, then suddenly I get harmonic distortion because I'm dividing by an envelope. Oh, you don't really hear it as harmonic distortion just yet, but at some point you'll hear substantial harmonic distortion. Right? That's really no sinusoid. That's something else. Okay. So, and this is a 400th of a second. I really want on the way up, I want the slew limit to be perhaps something very, very high, like 20,000. Right, now let's look at what that's doing. And now I'm going to compensate by making the slew rate on the way down be, say, 1/10 of a second. Well, actually even a half second. Like that. 2 per second. And now the deal is, it works so in one cycle of this thing, which is 1/220th of a second, it works its way down very, very slightly, but then it instantaneously gets slapped back up to the peak as soon as the next sinusoidal peak comes up. So what this really is a sawtooth, which gets pushed up when the sinusoid hits its peak, and then drops down by, well, let's see, I said 2 per second. So in a half second it would drop, it would lose all of its value. And it's 220 hertz, so it's losing 1/100th of its value, I think, if I'm doing that right. It's 1/200th of a second, so there are 100 of those in a half a second. So it goes down by 1% and then gets whacked right back up to where it was before. So if you looked at this thing, if you looked at the waveform that was coming out, I don't know if we'll be able to see this, but you should be able to see a little kink right at the top of the thing where suddenly it went up and then it just got no every single time, no, and then it starts, and then so it's getting turned up very gently while this thing is going on, and then getting suddenly slapped back down right up here. And the result is not too distorted sounding. The sinusoids, by the way, are the easiest things to hear distortion in. So if we try this in a drum, say, we should be very happy. Let's see, let me get a drum out. I said I wasn't going to do this, but I guess I really have to now. So what I'm going to do is I'm going to go look for the thing which... Is this going to be a good idea? Of course, the thing that I test it with is real, but I don't want to use my compressor. This is me making a compressor, but doing it. Sorry, this is a fully achieved compressor, of which this is a sketch. What I'm going to do is I'm going to borrow my stuff from here. No, I'm just going to use it from here. Let's see, sound file, loop time, start metro bang. So now we're listening to this. Nothing. Oh, here it is. All right. That's out of some free sample set. Actually, that's not a... I would like something a little better than that. You know what? I'm not going to go looking for anything better. I'm just going to live with that, with what that is. Okay, now we're going to take that and we're going to send it to anything. And now we're going to forget about this patch and just enjoy our poodle over here. And what are we going to do with this? We're going to do what that was. In fact, I'm going to just lose this oscillator and hook the poodle up right there. Before I do that, everybody's turned off, right? Yeah. And now we have limited drum. I told you you're never going to want to do this. That's the drum stroke. Okay, now let's set about trying to make it nice. I think the deal is going to be, first off, let's turn this off for a second. So what we're doing here is a rather extreme setting for a compressor. What we've asked it to do is have a compression ratio of infinity. In other words, whatever goes in, I want to have unit gain out. Right? Totally reasonable, right? And this is what you get when you do that. That's the drum. Well, actually, maybe there's things wrong with it. I'm not sure. Oh, look, it's really sick. That's horrible. That's just not. Oh, look, there's a little signal in the outlet. Clip it. It seems like. Okay, so first off, just to see if we're doing anything reasonable at all, let's go back to. I'm going to turn this down a little bit. Let's go back to the reasonable slew on the way both up and down, but slower. There, we're starting to hear a drum. All right, you know what? This is painful enough that what I'm really going to do is do what I should have done earlier, which is add something to add a fudge factor here, which will limit how much it'll divide by. There. Didn't that make a difference? Okay, so now what I just did was I'm not going to divide the thing by its own amplitude so that when the amplitude goes down to 0, it divides by 0 in order to get the thing back up to 1. Instead, I'm going to limit below the estimate of what its amplitude is by adding a slight number to it, so that in this case, the most it's going to multiply the thing by is 25, 1 over 0.04. I was going to divide by something, but the something itself is going to be a 25th plus this amplitude estimate instead of the amplitude estimate. So it'll push it up a factor of 25, but no more than that. Because come on, what it was really doing was it was finding just the little tiny bit of, maybe it was reverberation in the room, and turning that into a full-fledged signal before, which was really not right. All right, and now what we've got is drum, but of course, what we would like to be able to do is compare that to the drum before it got compressed, which is here, right? Yeah. There's the drum going in. And here's the drum compressed. Not so bad. It's only one. Oh, yeah. I should give you both channels. Yeah, now I can hear it too. Okay. That's compression. And you can like it or you can not like it. What I should do is show you. Oh, no, let's not do that. I don't have time. It's going to show you the Peter Gabriel thing of doing the opposite and just letting it through when the thing goes up. But what we can do here, since we're now just doing a fixed thing of limiting, but we can now mess with changing the slew rates of limiting up and down to see whether we can make it do something more reasonable. So in particular, here we could argue that the attack there is losing I don't know what it's losing. Well, anyway, we could argue that it should react quickly to the attack and then go down less quickly. So first off, if we make this thing go very fast uniformly, then we get this. That's not bad, but it's distorted. And then the trick is to make it go up real fast, but not go down real fast like this. Yeah, there we go. Yeah. Maybe that's a little extreme, so. Yeah, there we go. Anyway, you can play with these things for hours, right? And it's even worse than that, because all I did was just give it a fixed thing to do here, but really what you would do is you would make a mapping of some sort or another, maybe using linear segments, between the measured inflow that you saw going in, the measured strength that you saw going in and the strength that you want going out. And usually people draw curves that are the dynamic curve, and that would take the place of this little fudge here. All I did was just sort of asked it to do a stupid curve. Questions about what I'm doing so far? I could go on and on, but this would be a good place to stop.
Could you co-opt this thing to do like trajectory computation?
Wait, what?
Sorry.
Say what? Yeah. Tell me what you mean, because I want to know.
Like calculating. I mean, obviously it's keeping track of like the rate at which things are changing, and then you could set it such that it.
Oh, so it had some momentum or something.
Yeah.
Is that what you're thinking?
Yeah.
Yeah. I think you could do that, and you just need a second order nonlinear filter to do it. And I've never done that, so give it a whack and see what see what it does for you. Other questions? Yeah.
Yeah, just to go back to the flexitone example.
Oh, yeah.
Would that be an example of an oscillator coupling with itself? Is that kind of what's happening there? Flexitone? No, it was the other one.
Yeah. No, I think it is the flexitone. The one that simply has different rotational speeds depending on radius.
Yeah.
I need to think about that. I don't think it is. I don't think it's the lowest order possible thing that you could do. In other words, I think that's actually a fourth order effect.
Oh.
Fourth order effect, like a fourth power effect instead of a third power one, which are the simplest ones. I haven't shown you anything third power because none of them are nice and symmetrical and simple like that. I have to think about that and make sure I'm not telling you a lie there, but I believe if you had an oscillator coupled with itself in that sense, what you would do is you would push it north on one side and south on the other, so that the X thing would increase the speed at which it was going.
I see.
And here we're doing that, but we're also doing that. Maybe it is. Maybe it's just two dimensions of self-coupling added. Maybe. I have to think about that. Yeah, I'm going to go back and at some point in a couple of weeks, maybe I'll inflict the quaternion oscillator on us here, and then it'll maybe become clearer. So that's looking ahead. All right. Time to go. Next week might be a holiday. I think it's President's Day, or is it